Hello and welcome back to AB1202 Statistics and Analysis Week 12 tutorial. In this video, we'd like to talk about simulation concepts, what are the basic ideas and goals, right? And then we want to look at the core of everything under simulation, the inverse CDF function. And after understanding that, we will talk about generating random numbers. Okay. All right, let's get into the agenda itself. For simulation is a clever methodology that exploits all the goodness of computing, mathematics, and applications. More specifically, computing refers to computer science, computer technologies, chip, wafer manufacturing improvements, Moore's law, right? The never-ending cycle appears that every depends on who you talk to, 12 months or 18 months, the number of transistors in a fixed chip area will double. And that's exponential, right? That's exponential in nature, which is at first not that fantastic. It just means, oh, great, right? That's good, advances in technology. But then after some time, as you understand the exponential curve, right? After some time, towards the right part of the exponential curve, it starts to get really crazy because um, you start to have such huge computing power that computer can even generate real-time images, high-resolution real-time images on the fly, right? And even video on the fly, and that's amazing kind of computing power that doesn't come along with ease if the manufacturing technologies for chips and wafer plants and all that didn't get improved. So it is like the whole society is moving towards being able to digest data and even resynthesize data, right? Which is what simulation is all about. Better and better. So for that kind of technology, you need to have good support of fundamental theories, and that is from mathematics, more specifically statistics and probability, and that's where we are here for. And in particular, the part of statistics that deals with simulation a lot is in the inverse cumulative distribution function part of it. So we'll discuss a lot more in that. But right now, let's understand the whole idea of simulation, right? So it's made up of computing. We talked about that. It's supported by mathematics, right? We also talked about that. We have a lot more to say about that. And also, this great stuff has to find meaning in real life. For otherwise, it would just be great and beautiful and kind of a bit useless. But it's not, right? But it's fantastically useful. Um, and so there is this ease of applying it in real life thanks to mathematics and models that allow us to translate real life parameters, data, measurements into digital form for the computing technology, for computers to manipulate the data, resynthesize the data to get insights and then visualize it for us in the screen, in the monitors, right? So that's the basic concept of how simulation works in the macro perspective. But what is it for? The idea of simulation is different from the idea of, say, discovering the parabolic equation of a free flying object on Earth, following Newton's law, right? And that's parabolic. And that is just a formula. What's so different about simulation is that we are at times unable to find out or even give an estimate of a macro behavior when we do know the micro, I mean, micro doesn't have to be very tiny, micro components, the components are well understood. But when put together, whether in tens or thousands or millions or even billions of them, the collective behavior, what I would refer to as the macro behavior, is kind of lost in the transit, in the details, in the formulas that we cannot even manipulate because there are too many of them. The interactions and the in between, right, the mutual and pairwise interactions, they're just so enormous in complexity and combinatorial explosiveness that we just cannot handle in plain formulas anymore. But computers can, right? So computers is a little bit like GPUs. Each and every tiny unit in the GPU is capable of doing very simple arithmetic, which are well understood, right? Multiplication, addition, subtraction, division, right? So all these are well understood, and they are thoroughly checked and very well implemented in GPU. And sometimes what we need to do is to do ray tracing, right? And do model coloring based on the shadows and different shades of the colors under different lighting conditions and all that. And those are basically millions and millions of repeated same calculations. And that's the way GPU works, you know, which is to just follow each ray by each unit within the GPU. So similarly, we think of simulation as trying to track and mimic each individual entity and particle in real life, so that when put together in a way that we want, whether by design or by planning, we can understand the macro behavior. Okay, just one step forward in an example. We may know the air particles, right, from physics, from chemistry very well, right? The air particles from geographical studies, we know air particles very well. We know how it moves. We know how it will provide friction and so on and so forth, right? When billions of air particles are put together, like each air particle is 1 millimeter cube of space, right, containing air. So when 1 billion of them are put together, how does it affect, right, the weather? So then we can use that to forecast weather. And if we can mimic each and every air particles well and compute fast enough, we can then predict, right, weather further and further into the future. And those of you who know, weather forecasting is often very difficult because, you know, it's the butterfly effect, right? So tiny little changes here and there can affect eventually the entire weather system. So how to track all these by a single formula? That's not quite possible, or even a system of many equations, still not very possible. And therefore we use simulation. We don't need to worry about the interrelationship between equations. We just care about fully describing, all right, our full knowledge of each air particle, that 1 millimeter cube of volume, all the physics, all the chemistry, all the whatever geographical properties that we know of, we program it into that air particle. And then we let the simulator work by letting all millions or even billions of these interact with each other and see what happens, right? If it rains, right, says this model, then we can say, well, in the half a day's time, there will be rain. And surprising enough, this tends to give pretty reliable outcomes, right? So, of course, weather forecasting remains a challenge. But let's look at another example. We are going to build a building. In Japan, for example, it's very susceptible to earthquake shaking. And the building has to sustain certain levels of, shaking and should be able to tolerate it without even cracking, right? Now, we have a new building because the architect has, special design to make it commercially very attractive. But then will it withstand the kind of regulatory and of course earth requirements that it will not fall, it will not collapse when there is minor earthquakes, when there's minor shaking. Now we cannot build the building first because that would be the entire budget, right? The $500 million to build the project, that is the only budget available. We don't have multiple such budgets. So computer simulation or CAD/CAM design, if you have heard of it, computer assisted design, CAD. CAM is computer aided or assisted manufacturing, CAM. These are basically digital twins of that real life big project, big building that we're going to build and we haven't built. And we wonder, right, this macro object, because it's built up of cement, steel, beams, right, and platelets and plates, right, so building plates. And we understand those very well because we build them. They are components that we can stress test and even destructively test and measure each and every piece very accurately, very thoroughly. So we know the components very well. But when put together as a building, will it collapse? That's our macro question. So now you can get a feel that we oftentimes are faced with knowledge about the components, very good, 100%. But when put together, these components in great numbers, thousands, millions, billions, we don't know what will be the systemic output, what will be the macro behavior. So these kinds of questions are very, very suitable for simulation techniques to be applied. Okay, now so that's about the building. So when we build a digital twin in the simulation software, we can shake it digitally, all right, and then if it collapses, we'll rather take it, play it safe, right, because there can be a mistake that actually the building is safe, but then the computer digital twin model shows that it collapses. So we play it safe. If it collapses, we just don't want this design. But if it doesn't collapse, then the simulation software at least has made a very intensive test of this design. Doesn't imply that it is fully sort of resistant to shaking yet, but at least it gives us a lot of confidence now. So we might want to build a small model first, a prototype, to see if we actually shake it, will it tolerate, will it be able to withstand the kind of shaking, right? And then gradually we can build the final building. So that's the macro behavior. One more example, drug discovery. Okay, so this time the drug we're talking about, the macro we're talking about, is so small that our eyes cannot see. So we're talking about, let's say, finding or discovering a new COVID-19 drug that can cure COVID-19, not just vaccine. All right, so is that you are tested positive for COVID-19, you have fever, you're not feeling well, you take this drug, and bingo, you're okay. Right? So it's a magic pill. But can we synthesize it? So again, we know the even tinier components very well. We know the amino acids, we know the proteins. Individually, we can isolate them in the labs, right? And then test them thoroughly and know even their shape, molecular structure, electronic behavior, and so on. The question is, when we synthesize them, put them together, will this new drug be a poison, right? Or will it be a non-poison, but it's not effective, and that will invalidate the claim of this new drug being able to cure COVID-19 patients, right? So you are attracting legal lawsuits. So ineffective or not, poison or not, we can simulate. And once it is shown to be non-poisonous, effective, then we say, is there another combination, right? Is there another design of the drug, combination of the amino acids and proteins that will make it even better, even less side effects, and so on. So we can simulate some of these, but ultimately, when it passes the simulation tests, right, used by pharmaceutical companies and all that, you still don't know whether it actually will work. So we still have to do actual clinical trials, just like the building after passing through the CAD/CAM earthquake shaking tests, right? The simulated tests, we still have to prototype maybe a few stories first or something like that, or simulate the load first and in real life before we actually build the final building. So same thing, before we go for mass manufacturing of this new drug, let's do a few clinical trial. Out of 20 patients, 17, 18 of them show very good recovery. So there's effectiveness, there's efficiency in the new drug. Okay, great. We are very confident, and so on and so forth. So I hope the range, right, the diversity of the applications of simulation in serious business applications have been able to convince you of the tremendous value, right, in simulation. Whether it is in terms of reducing costs, right? For example, we can shake the digital twin. First, that's simulation. That's reducing cost, because otherwise you have to build a new building. And for that matter, it just reminds me, for CAD/CAM manufacturing of cars, there is this crash test that is mandatory, right? So the car must survive certain level of crash at certain speeds and from different angles. Now, if you do a actual car crash test, it is eventually necessary. But then if you can simulate it first, at least you will save a lot of test runs that will be very costly, right? If you have to even just you know, run the car without so far, without leather, without any measurement instruments, just the car itself, right? And the engine, that will still be very costly if you have to do it many times to get it right, for example. But then if you can simulate the digital twin of this new sports SUV vehicle that this automobile company has started, you can digitally ram this digital twin version of the newly designed car onto the wall and see what's the damage, because we know the steel beams very well, we know the weight of the car, the weight of the engine, and we can put them together and then digitally crash it, right? And digitally analyze the wreckage to see what parts should be improved to protect the driver, to protect the passenger, and so on and so forth, right? And where should the airbag be? How strong must the airbag be? And when you are done, it's still not foolproof. You still have to build the actual car and run it. But then now, right, the confidence is a lot higher that if it passes the digital twin simulated test, it should more or less, right, unless there's sort of a blind spot, the modeling has some error or mistake. But otherwise, it should be also a smooth run. All right. So if it's able to tolerate certain level of crash, the actual car should also do the same. That's the beauty of it, and saving cost, saving life, saving many things, right? So simulation, of course, brings up the word simulator, and simulator basically started with the very expensive training of pilots. And so with realistic simulation of actual sky and even actual cities these days, even in the day and night, right? Because nighttime the city looks different, and it may not be the same memory image that the pilot has been trained for in the day. So there are now very realistic simulations that can help the pilot fly or take off or land, because these are the critical moments, in the day, in the night, many times. If you fail, you just like put another dollar and run another computer game. Simulator is a serious business, but the way it's being designed is just like another computer game. And for that matter, all computer games are simulations. The aliens that attack you, right, from the top of the screen coming down, and you are at the bottom of the screen defending your planet or your city. The aliens cannot be all coming down at the same time, right, at the same rate, left, right, marching like robots, because then it will be very predictable. It'll be then very boring, and then the game will not be very exciting and won't sell. If it won't sell, then the company basically close shop, right? So game is actually one that has to balance the use of random numbers in simulation very, very expertly, because too simplistically it is boring. Basically, the robots, the aliens are like robots. They are very predictable. Every 3 seconds there'll be one alien coming up. So as a player, you already know what to expect, right? Uh, but too complicated. If it's chaotically random, right? Totally unpredictable. Then even the best player will give up because it's so hard, right? And there's no pattern to it, no rhythm, no secret formula, and that will be very discouraging. And again, it won't sell. So too easy, no good. Too hard, no good. And game companies, those that survive, those that thrive, they are experts at balancing the use of random numbers. And therefore, the very realistic looking games that you see, they are definitely right the very expert level of demonstrating how simulation works. Now, don't confuse simulation with visualization. Very different, right? So the goal of simulation is to generate data. Of course, you can combine it with visualization, just like computer games, and for that matter, Hollywood movies that are computer generated. And also, so we're talking about more and more examples like AI generated videos, short clips of videos. These are all simulation because the outcome is generated data, right? The produced data based on random numbers, based on weights for AI, right? Based on distributions. And combined with visualization or displaying, then we will show those numbers, because we cannot be shown with thousands and thousands of numbers. Our eyes don't catch the meaning. And so when displayed as pixels, as colors, we are borrowing our eyes and brains as a pattern recognizer, and be able to quickly extract, right, whether there's meaning, emotions. For example, our eyebrows, we are angry, we are sad, right, we are boring, and so on. So we can extract patterns, we can recognize emotions, we can seek out contrasts very readily based on our high-tech sensors called the eyes. So visualization, the goal is to borrow our eyes and brains to analyze, to extract information. Simulation is not necessarily using our eyes and brains, but then the focus is on generating uh, accurately random numbers, accurate random numbers based on accurate description of the probability distribution. Okay, so that's overall idea of simulation and what it is not when it's compared with visualization. So I've spoken a lot about the concepts, right? And a lot of examples, and I hope you can now begin to have a feel that simulation is everywhere around us. And what is it all about? It's mainly about the inverse cumulative distribution function. So the idea is, first of all, the cumulative distribution function of x is defined as the probability of a random variable being less than or equal to x. So this applies to whether you have a discrete distribution for capital X, or a continuous distribution. And for inverse CDF, right, if we call CDF of X the number Q, because Q will be a number between 0 to 1. Cumulatively, the probabilities will add up to 1 at the most, and at the least, it will be 0. So the inverse CDF of Q is going to be, that's right, not surprisingly, X itself. So in other words, the inverse CDF of the CDF of X is just X itself. Just like arc sine is the inverse function for sine. So arc sine of X is X itself, provided X is in the right range. But is arc sine the inverse function for cosine No, those of you who have seen it, right, it will be arc cosine. So same thing here, the inverse CDF is just a generic term, it's just the inverse function. We need to talk about what is the shape of x. What's the shape of x? Yeah, the shape of x, in other words, the distribution of x, if it is normal distribution, the inverse CDF function will be one functional description. If it is uniformly distributed, continuous uniform distribution, then it will be another function. So inverse CDF is just a generic term to talk about talk about inverting, right? Inverting from the CDF value back to the original x value. Now, let's just backtrack a little bit, all right? Suppose I sell sugarcane. In Singapore, there are many sugarcane juice stores, and I sell out 9, 10, or 11 boxes. I didn't know until I started to measure, right? So I started to count the boxes, and let's say there's no day when I sell 8 or less, and no day when I sell 12 or more sugarcane boxes, right? So each box will have a lot of sugar canes, and these months are hot, so I sell a lot. But it will always be 9, 10, 11. But are they all equal? That means, is it true that if I take 9 days, 3 days will be 9 boxes, 3 days will be 10, 3 days will be 11? Not necessarily. So I started to accumulate the boxes. Okay, I start to randomly select a day, and I for that day I counted 9 box. Right, so I put a Lego toy block there. Right? Is that okay? Right. So if I counted 9 box, that's one day, right? One day where I counted 9 boxes. So there's one Lego toy block. And another day I counted 11. So that's another one. Yeah. And I keep doing that. So some days there'll be 10, and I counted 10 again, and I counted 10 again, I counted 11, I counted 10, I counted 9, and as you can see, I keep doing this, right? I stack up and I randomly pick 10 days, and I ended up with this. And that is my histogram, isn't it? Because that's basically how measurement works. So if I write it as frequency, this will be 1, 2, 3, 4, 5, right? But I choose to take it as a sample size of 10. So 2 divided by 10, basically that just means 0.2 and 0.3 and 0.5. So the probability of x is given by the y-axis. If I assume future consumption of the sugarcane boxes will follow the same proportion and weightage. So now we can just assert that the number of sugarcane boxes per day, right, the probability distribution will follow this strictly. That's my probability distribution here, discrete, right? So the height is the probability itself. Now, if I ask, what is the CDF of of 10? Answer is 0.2, yeah, because it will be the probability of all x values that are less than or equal to 10. So 9 is less than or equal to 10, so I have to add this 0.2 here. 10 is also less than or equal to 10, so I have to add the 0.5 here. So answer is 0.7. How come I don't add 11? Because 11 is not less than or equal to 10, so I skip adding the 0.3. So the answer is 0.7. Okay. So that's just one example, and of course you can try with asking CDF of 9, CDF of 11, CDF of 8 is 0, because at 8 I see 0 probability, so, and I stop there, right? So it's 0. Okay, and then what happens? Well, Well, let's derive a CDF chart. Okay, so a CDF chart is going to be sharing the same x-axis aligned, right? So in other words, the 9 is the 9, the 10 is the 10, the 11 is the 11. But the vertical axis will be a CDF, will be cumulative distribution function. So it will range from 0 to a maximum of 1. So it starts from 0 and it should reach 1 at the most. Okay. So let's begin by asking, what's the CDF of 9? Well, that's 0.2. That's it, right? So we will, let's call this 1. And so this will be 0.2. And so the CDF of 9 is 0.2. Actually, just a dot here. The CDF of 10 is, we have already calculated, 0.7. So that's 4, 6, 7 around here. And the CDF of 11 will add on to the CDF of 10, the 0.3. So that will complete the 1 here, right? So it will be a 1 here. You can, of course, draw the vertical lines, but they are not necessary. Okay, they are just there to kind of show some similarity, but actually not. It's just the dots here. Okay, so what is involved is that we are now able to say what is the inverse CDF. Okay, so this is the CDF. Did I say CDF? Yeah, so this is CDF. Okay, this is 1. All right, so the inverse CDF of the above. If I use the CDF chart here and to ask the same question, what's the CDF of 10? You notice that I don't need to add anymore because they have been added. So I just do a table lookup, right? CDF of 10 is going to be 0.7. So answer is directly 0.7. Just do a table lookup. Now, if I say what is the inverse CDF of 0.7, I'm sure you agree with me, right? Because we have been working on this example, that it will be 10, right? It will be 10. So we can just swap the values, because what is the rightmost value such that the probabilities add up to 0.7? Well, no larger than 0.7, because the definition is less than equal to 0.7. No larger than 0.7. And so the answer is 10. Okay. Well, but we can also see it as, instead of going upwards and then looking at a 0.7 as the answer, because it's table lookup, we now point the beam backwards. It will be, we start at 0.7 and we shine the beam backwards, right, into this line, and we'll, because it's at the line itself, we will go into half of this horizontal segment and then drop down, so the answer is 10. That's the reverse lookup, which is the what inverse CDF means here by calculating inverse CDF of 0.7. It just means first start at the y-axis, then find the value of the x-axis that corresponds to the y-axis value. Okay, so that's the whole idea here. Now, what if we have inverse CDF of something else? Let's say 0.6. Then what happens? Okay, then what happens? Well, in this case, 0.6 is a little bit below, right? It's a little bit below 0.6. Then same thing, we shine a beam, a laser beam or something, which will hit the wall here, all right? And it's going to fall down. So it's going to hit this wall and gets either reflected down or drops down all the way. And you can associate this with, because it is hitting 0.6, right? It is hitting the wall between 9 and 10. So it is a little bit more subjective. So now what we need to do is to do trial and error. So the CDF of, if the answer is 9, we would have accumulated 0.2. If the answer, if we try, the answer is 10, we would have accumulated 0.7, right? Yeah. But 0.7 is the first number that is just larger than 0.6. And so we can associate it with 10 as well. Okay. Okay, so that is the discrete distribution for x, and we talked about how to calculate or identify the CDF, the cumulative distribution function, building up from P of x to a CDF chart like this, and then the inverse, which is like a reverse laser beam, right? Starting from y-axis instead of x-axis, and then come down. So to randomly generate data, what we want to do then is to be able to have a random number generator, right? To randomly generate a number, a floating point number, a real number, anywhere from 0 to 1. Yeah, okay. So this will allow the range of the y-axis to be fully covered in a uniform way. In other words, any number on the y-axis has equal probability of being landed upon. Let's put it that way. So if you imagine this is a lift, right? At the press of a button, the lift will randomly stop at any height, even jam in between floors, and it will stop there. Then we say calculate that inverse CDF of that height. It will be then giving us a value that will be either 9, 10, or 11, which will then correspond to our consumption of sugarcane boxes for a random day. And that is nice because our consumption never will be 8, 7, 6, never will be 12, 13, 14. And so the range is correct. And also because this height here, right, giving 10 as the outcome, is going to be very much larger than the height of 9 and the height of 11. And so you can see now that 10 will appear most of the time. How frequently? 50% of the time. All right, so you can then generate it and you will see 9, 11, 9, 10, 10, 10, 9, 11, 9, 10, 9, 10, 10. 10 will appear most of the time. And if you plot a histogram of those random numbers of 9, 10, 11, you will recover this, perhaps with a bit of dents here and there, but essentially this shape. Then that is the whole idea. We have successfully controlled the generation of random numbers that conform to this particular distribution. Okay, so that's the whole idea of simulation. Generating random numbers through the use of inverse CDF in order to achieve the goals required at the start of our simulation, which is to understand the macro behavior. Okay, so that's for the discrete distribution. Now, what if we have a continuous distribution like normal bell curve? Okay, this time round, bell curve is completely symmetric. It's not like a left-skewed distribution like in this case. So we can also say that our consumption of sugarcane boxes has a mean value of 10 and a standard deviation of 1, let's say. One box. Right? So on a random day, it will be on average 10 boxes with a standard deviation of 1 box. So now calculate the CDF of 10. Calculate the CDF of 10. All right. Now you can use Excel or you can use R, and the answer is, first of all, we say X is following normal with a mean of 10 and a standard deviation of 1. Right. So you can use Excel, you can use even your TR-84 calculator, or you use R, and the answer is going to be how much? 0, well, CDF of 10. So in R, you will use P norm, right? So the mean is 10. And of course, you guys have already seen, without calculation, that's half. Just now it wasn't half because there's a bit of a skew, but right now it's right in the middle, right? So CDF of 10 is exactly in the middle and it's half. So not surprisingly. Then let's try to build the CDF curve. Again, we need to have the x-axis aligned because the what we call the domain here ranges from -infinity to infinity. They all make sense for normal distribution. They don't make sense for our discrete distribution, right? Because only values 9, 10, and 11 are valid. But for normal distribution, the entire domain from -infinity to infinity makes sense. So we will have to shift our y-axis now to be at the mean here, because at 10 here, we should reach 0.5 because we have calculated that, and also because we know our bell curve very well, right? So at mean value, it divides the bell curve into 2 exact halves. So what it means is that the CDF will pass through 0.5, right, and then gradually strives to reach 1 at infinity, and it will touch 0 at -infinity, and like this. So this will be the bell curve. So now again we can ask questions like, what is the CDF of 10? And it will be a lookup, because at x equals to 10, we look up and we get the y-intercept at 0.5. So our answer is 0.5. So again, same question. If we ask what is the inverse CDF of 0.5, then answer is 10, right? But following this, suppose we ask what is the inverse CDF of 0.6? Well, either we integrate the PDF of normal distributions function from -infinity until 0.6, until 9, until 9.1, until 9.2, and then try to interpolate and try out trial and error method, or we use software, right? So in R, it will be Q norm to find the inverse CDF of a normal function. So the Q norm of 0.6 with a mean of 10 and a standard deviation of 1 is going to be, I hope you're doing it now, 10.25335. So 10.2534. No doubt, in real life, we will not be consuming 10.25 boxes of sugarcane. It's either you open up the 11th box and take some or not. Nevertheless, to the extent that 10.25 means we are breaking open the 11th box and using some of it and not all of it, it does make sense, right? So long as it makes sense, we can interpret it in real life, then okay, we are okay with it. It's a bit like X is our salary. So our salary is never going to be $10,122.335784 cents or dollars. I mean, it won't be going to the third, fourth, fifth decimal places of a dollar, right? However, so long as it makes sense, right, in real life, we can interpret those decimal places in the third, fourth, fifth decimal places as less than of a cent. right? And it's not so consequential, so we can truncate it without worrying too much about of the truncation losses. Then it is okay that we approximate the real life salary with a continuous line. So it is similar in terms of interpretation here, that the decimal places don't really mess up our interpretation here. Okay, so um, next, what we want to do is to do a quick uh, discussion on the another distribution that is commonly seen, which is the uniform distribution. So suppose we are talking about the uniform distribution, and it ranges from 9 to 11. Okay, so 9 to 11, and it's continuous. So right, so we need to take into account the end effects. So in this case, since actually we want 9 to be in, so this 9 becomes 0 probability. We should also include 8. So let's just extend it a bit, right? From 8 to 12. Okay, what's going to happen? Well, first of all, this whole area needs to be adding up to 1, right? Yeah, because then it will be a distribution. So first thing first is that x follows uniform distribution from 8 to 12. So what does it mean for the height? The length is 12 minus 8, 4, and the whole area of a rectangle has to be 1. So it has to be 1/4 here. Can everyone see that? Okay, so then it will be a distribution. Now, we ask what is the CDF? What is the CDF of 10? Not surprisingly, it's also in the middle, so it is 0.5, right? But another way to find out is we find the area of the rectangle, which is to integrate 1/4 from 8 to 10. But integrate 1/4 means find the area under the horizontal line 1/4, which is 1/4 height times 2. So that's 0.5 again. So not surprisingly. This time round, let's build a CDF curve. And then we can now expertly do it a bit quicker, right? Because we understand the mechanics now. So first we have to align the axis. Then we know this from this simple point here that at 10, we should pass through 0.5, right? And then at how many? 12, we should reach complete 1. So that's going to be a 1 here, right? And at 8 and below, it will be 0. So CDF will be 0 from 8 and below. So it then builds up the area gradually and continuously, right? And uniformly. So basically, it's going to be a line touching 0.5 at x equals to 10. So that's it. So this is the S curve in a very linear way, linear segmented way. Okay, and we can again ask the same questions, right? So what is the CDF of 10? We look at 10, we shine a beam upwards, it reaches 0.5, so answer is 0.5. But let's make it more interesting. What is the inverse CDF of 10? Of 0.5? So we start from the y-axis, 0.5, and we basically shine a beam downwards. What's the x value correspondingly? It's going to be 10. So same thing here. What is the inverse CDF of 0.6? Which we don't know. So we need to go to 0.6, shine a beam downwards, right? And essentially to calculate using the general inverse CDF function for uniform. So the general inverse CDF function for uniform distribution of from A to B of Q is going to be A plus the width B minus A times Q, or magnify Q by B minus A multiplier, then add an offset of a to it. So what we have here is 8 plus 12 minus 8, that's 4, times 0.6. So 4 times 0.6, 2.4, plus 8, so that's 10.4. So answer is 10.4. So in other words, this is actually not so far to the right, but 10.4. Right, so this is the inverse CDF function for uniform distribution. And if it is not in Excel or in Python or whatnot, you can just calculate using this, because the inverse CDF function is so simple. Some inverse CDF functions are so complicated, right? So let's just wrap up a little bit here. So suppose we have so what we want to do here is to have a R function. So suppose the CDF table, this is a CDF chart, but in quizzes and exams, questions usually don't come with charts because they're difficult to draw, difficult to produce, and what is more likely is that you will see a CDF table like this, right? So the CDF and the X. So assuming you have a 0.0 corresponds to 9, 0.2, and why 0.2 is because the cumulative distribution function gets from 0 to 0.2, the height, right? That is going to give us 10, and then 0.7 is to give us 11. So in Excel, you will use this table in a VLOOKUP, right? So in Excel, you will use a VLOOKUP of the value, comma, the table, comma, column 1, column 2. So you return 2, and then true, where the true will instruct VLOOKUP to go for partial match, so that 0.6 is not found here, but the so-called largest value of CDF that doesn't exceed the given 0.6, which is 0.2, not 0.7, will make VLOOKUP return the second column of the table, which is 10. So that's going to give us what we want. In R, all right, there is not a VLOOKUP function, but then we can just call this a data frame. A table is a data frame, and suppose the variable df has already read in this table, then what you want is just to do a tail of the df. Okay, basically it is row comma column, row comma column. So you can say df row. What are the rows? The rows are those df table, the df tables of the CDF. You can do a $CDF, or you can do a square bracket CDF. Right. These values which are less than the given value 0.6. So you can replace 0.6 with any other CDF value. So those are the rows that qualify. Which are the rows? 0.0 qualifies, 0.2 qualifies, 0.7 out. Right. So it will be 0.0 and 0.2. And from these, we don't want the whole row, which consists of 0.09, 0.2, and 10. We don't want. We just want the column X. Okay. So at this point, we will be extracting the vector 9 and 10. Yeah, 9 and 10 up to here. And we say take the tail, the last one. That means we just take the last value 10. So that will give us 10. So you put a 0.6 in there, the answer is 10. Because it's the last row, which is the largest possible value that doesn't exceed 0.6 given on the first column. Okay. Now, similarly, for the normal distribution, in Excel, this we need to invoke the native function norm.inverse of 0.6, comma, the mean, which is 10, and standard deviation 1. Right, so norm dot inverse will give us the answer right away. In R, we also have a similar function, that's Q norm. So we just enter 0.6, comma, 10, comma, 1, finish. So again, it's going to give us the same value. For the uniform distribution, what we want is to, in Excel, there is no built-in function for that. So we just do what we need to do here, A plus B minus A times 0.6. And you replace 0.6 with any other value. And the A and B, they are the 8 and the 12 here. In R, you can use Q unif, right? Or just simply A plus B minus A times 0.6, same. And Q unif is to give us the same calculation, I think, yes. Okay, so, or Q unif 0.6, comma, A, comma, B, which is the 8 and 12. Okay, so we have, by means of 3 different distributions, right? The discrete and also table distributions that you will see very frequently in exams and quizzes. The normal distribution, which is by and large encountered very frequently in theories, and the uniform distribution, which is a very important seed distribution in simulation, right? What do we need to do now? Because up to here, we only calculated inverse CTF. So here, the main idea, the main idea, right? So is as follows. So all these are good and nice, but we are not doing simulation if we didn't provide one important replacement, and that is to simulate, right? Replace Q with a random number generator. So in Excel, let me move myself away. Okay, so over here, right? So in Excel, we will use the rand function. So whenever we talk about 0.6, where is it? 0.6, the 0.6, right? Anywhere we talk about the 0.6, as I use the example, replace it with rand, and you will then be getting a whole bunch of numbers from the fixed static formula. The formula doesn't change, but every time you run it or evaluate it or press F9, you will see the number being updated. Sometimes 9, sometimes 10, sometimes 11, flipping back and forth in a random fashion. Or what you can do is to copy and paste the formula across 10 or 100 rows, and you see that all the numbers are different. Right, so this is how the magic works. So replace Q with a random number generator that is found in the language. So for Excel, it is just the same spelling, rand. All right. In R, basically similar, but we are going to just use the continuous uniform random number generator. So R unif, and give us one such number. It's capable of producing 10,000 numbers if you put 10,000. But if you put R unif 1, it's going to give you one decimal place number between 0 to 1, just like rand does. Okay, so replace Q with random number generator, essentially. So these are the building blocks, right? So once you do that, then essentially you will be getting a lot of random numbers that will conform to the given distribution, right? So in R, replace all the 0.6s that we have seen earlier, like for the discrete distribution, replace this 0.6 with the R unif bracket 1. So it'll be quite a long expression, but every part is very clear. Yeah. For normal distribution, replace the 0.6 here with the R unif of 1, and then you will be getting a bell curve. And for the uniform continuous distribution, replace the 0.6 here or the 0.6 here with R unif of 1. You will be getting an elongated uniform distribution that is going to satisfy the range requirements. So we basically have covered 3 examples and the whole idea, concept, thinking, and purpose of simulation. And I hope from this video you have a better appreciation of the power and simplicity at the same time, right, of applying simulations to solving problems. Not all problems are suitable to be solved using simulation. I mean, if you apply simulation to everything, it could be that you are solving the obvious. That means the answer is already clear. You're doing what is totally unnecessary because you already know the answer. But a lot of times, like I said, we know the components, principles, theories, formulas very well for the basic components. And we want to answer the question when many of these components are put together, such as in the building design, in the design of a drug, right, in the so-called design or construction of the weather, air particles, air systems, everything. Right? We want to know the macro behavior. So in business, it can also be that we know the demand, right? The demand of my sugarcane boxes for a single day very well. It's from 9 to 10 to 11. And the distribution follows this proportion. I know it very well. But if I operate this for a year, that means for 365 days, will I be profitable or not? That's a very important macro question. So it's not very sexy because you don't have fanciful graphics, pictures, movies, or visualizations. It's just a number. Will I be profitable? How profitable would that be? So it's just going to be a number. But this number involves the life and death of your business. So it's superbly important in your context. So how dare you not simulate, right? So you know the day-to-day business very well, but you don't know after 1 year how healthy or bad will your business become. That's why we need simulation, right? To time compress the day-to-day behavior and then be able to quickly see the future within seconds. That's the power simulation brings to us. You may want to say this is forecasting, but in slightly different fashion, because forecasting, you sometimes don't need to know the principle. You just go by a bit of correlated behavior, find a formula or find a pattern, then you can somehow forecast without knowing the why. But simulation goes a lot deeper, You might need to know so-called the physics of things, right? You might need to know the underlying consumption demand and profits and cost, fixed costs and variable costs. You might need to know a lot more. And since you know a lot more, you feed into the system a lot more raw material and understanding of the reality. The simulated outcomes, even though it's simulated, is going to be much more convincing, much more reliable, and hence much more useful for important decision-making processes. Okay, so with that, I'm going to just end there, and I hope you will have a lot of fun playing around with simulation. Thank you, and see you in the next video.